What if I told you that right now, as you sit watching this video, time isn't passing at all for the light hitting your eyes? That from light's perspective, the entire universe, from the Big Bang to the heat death of everything, occurs in a single eternal instant? And what if the reason we experience time at all is because we're moving too slowly through space? Here's something that will fundamentally break your brain. Every photon that has ever existed, from the first light of the universe to the glow of your phone screen right now, experiences zero time, not little time, not fast time, zero, complete, absolute, eternal now. And this isn't science fiction or spiritual metaphor. This is what Einstein's equations actually tell us happens at the speed of light. Think about that for a second. The light that left a distant star 13 billion years ago and just now entered your eye? From that photon's perspective, no time has passed. It was emitted and absorbed in the same instant. The entire 13 billion year journey you perceive, that photon never experienced it. Time, for light, doesn't exist. But here's where this gets absolutely mind-shattering. If time stops at the speed of light, and light connects every point in the observable universe, could it be that time itself is just an illusion created by our inability to move at light speed? Are we trapped in a prison of slowness, watching a movie that light experiences as a single frame? By the end of this journey, you're going to understand why some physicists seriously argue that time doesn't fundamentally exist, why your past and future might be equally real right now, and why the universe might actually be a frozen, timeless block that only appears to flow because of our limited perspective. This isn't just going to change how you think about time, it's going to change how you experience every moment of your life. But before we shatter everything you thought you knew about reality, do me a favor. Hit that like button and subscribe, because YouTube's algorithm works in mysterious ways, and I want to make sure these reality-breaking ideas reach as many minds as possible. Also, drop a comment telling me what country you're watching from and what time it is there right now. I'm genuinely curious about where in space-time this message is reaching you. Are you in Tokyo at 3 a.m., London at lunch, Los Angeles at sunrise? Let me know, because geography and time zones are about to get a whole lot weirder. Let's start with something you think you understand: speed. You know that cars move at 60 miles per hour, planes at 500 miles per hour, and the Earth around the Sun at about 67,000 miles per hour. Simple enough, right? Speed is just distance divided by time, how far you go and how long. But here's the first crack in your reality. Speed isn't actually measured in miles per hour or kilometers per second. Those are just convenient shortcuts. The real measurement of speed, the one that describes the fundamental structure of the universe, is measured in what physicists call space-time intervals. Here's what that means. When you move through space, you're not just moving through 3 dimensions of location. You're moving through 4 dimensions that include time itself. And here's the kicker that changes everything. The faster you move through space, the slower you move through time. Not metaphorically, literally. Think of it like this. Imagine you have a cosmic speedometer that always reads exactly the speed of light, 299,792,458 meters per second. But here's the twist. That speedometer measures your total velocity through spacetime, not just space. Right now, sitting still, you're not moving through space at all. So you're moving through time at maximum speed. You're aging at the normal rate, experiencing seconds as seconds, minutes as minutes. But if you start moving through space, something has to give. Your total space-time velocity can't exceed light speed. So as your spatial velocity increases, your temporal velocity decreases. You literally start moving through time more slowly. This isn't theory. This is observed, measured, experimental fact. In 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airliners, one going east, one going west. When they compared these clocks to identical clocks that stayed on the ground, The flying clocks had measured less time, not because they were broken, because they actually experienced less time. The pilots aged slightly less than people on the ground because they were moving faster through space, which meant they were moving slower through time. The difference was tiny, just a few hundred nanoseconds, but it was real, measurable, and perfectly matched Einstein's predictions. Time literally slowed down for the people on the plane. Now, here's where your mind should start bending. If this is true for planes moving at 500 miles per hour, what happens at 186,000 miles per second, the speed of light? What happens when you're moving through space at maximum velocity? The answer is absolutely wild. Your movement through time drops to zero. Complete stop, total freeze. At light speed, time doesn't slow down, it stops entirely. This is called time dilation, and it's one of the most experimentally verified phenomena in all of physics. But we can't just take physicists' word for it. We can see this happening right above our heads. Cosmic rays, high-energy particles from space, constantly bombard Earth's atmosphere, creating particles called muons. Here's the problem. Muons are unstable. They decay, falling apart into other particles, with a half-life of just 2.2 microseconds. At the speeds they travel, they should decay long before reaching Earth's surface. Do the math. Even moving near light speed, they should only make it about 660 meters before half of them disappear. But we detect muons at ground level all the time. How? Because from our reference frame, those muons are moving at 0.98 times the speed of light, which means time is passing about 5 times slower for them than for us. What feels like 2.2 microseconds in the muons reference frame is actually 10 microseconds in ours, giving them plenty of time to reach the surface before decaying. And here's the really weird part. From the muon's perspective, time is passing normally. It still experiences 2.2 microseconds of life, but the distance it has to travel has shrunk. The entire atmosphere, which is about 10 kilometers thick from our perspective, is compressed to just 2 kilometers from the muon's perspective. Space itself contracts at high velocities. This is length contraction, the twin sibling of time dilation, and together they reveal something profound. Space and time aren't separate things. They're intimately connected, trading off against each other. They're two aspects of a single thing called spacetime, and movement through one affects your relationship with the other. Hermann Minkowski, Einstein's former mathematics professor, put it perfectly in 1908. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Space and time aren't two separate stages on which events happen. They're a unified fabric, and your velocity determines how you slice through it. Different observers moving at different speeds literally experience different mixtures of space and time. Your now is not the same as my now if we're moving relative to each other. We're carving different paths through spacetime, experiencing different presents, different flows of time. This is why physicists stopped talking about space and time separately after Einstein. They talk about space-time, a 4-dimensional structure where 3 dimensions are spatial and 1 is temporal, all woven together into a single geometric object. And if that seems abstract, think about this. GPS satellites orbiting Earth are moving at about 14,000 kilometers per hour and experiencing weaker gravity than we do on the surface. Both of these factors affect how fast time passes for them compared to us. If engineers didn't account for both time dilation and gravitational time dilation, yes, gravity also affects time, and we'll get to that, your GPS would drift by about 11 kilometers per day. Your phone knows where you are because engineers programmed it to account for the fact that time passes at different rates depending on motion and gravity. Time dilation isn't philosophy, it's engineering. It's infrastructure. It's the reason your navigation works. Now that we've established that time and space are connected, let me show you something that's going to completely invert your understanding of speed. Light doesn't experience time. But that's not because it's moving very fast. It's because light is the speed at which the universe itself operates. Here's what I mean. We tend to think of light speed as really, really fast motion. Like, if we could just build a better rocket, we could go faster and faster until eventually we matched light's 186,000 miles per second. But that's exactly backward. Light speed isn't a speed limit on motion. It's the conversion factor between space and time. Think of it like this. When physicists write down the equations of relativity, they don't use different units for space and time meters for one and seconds for the other. Instead, they measure both in the same units by using light speed as the conversion. 1 light second is about 300,000 kilometers. 1 light year is about 9.46 trillion kilometers. Time becomes a distance, measured in how far light travels. Why? Because light speed is the fundamental exchange rate between space and time. It tells you how much space equals how much time. It's like the number that converts dollars to euros, except instead of currencies, it's converting dimensions of reality. And here's the really crucial bit. This exchange rate is the same for everyone, everywhere, moving at any speed. No matter how fast you're going, you always measure light moving at exactly 299,792,458 meters per second relative to you. This is the constancy of light speed, the experimental observation that broke classical physics and forced Einstein to develop relativity. Think about how insane this is. If you're standing still and I shine a laser past you, you measure the light going 299,792,458 meters per second. Fine. But if you're on a spaceship moving at 150 million meters per second in the same direction as the laser, half the speed of light, classical physics says you should measure the light moving at 149,792,458 meters per second relative to you, right? Just subtract your speed from light speed. Wrong. You still measure it going 299,792,458 meters per second. Exactly the same speed. How is this possible? Because space and time themselves adjust to make it work. Time slows down for you. Space contracts for you in exactly the right proportions so that light speed remains constant. The universe literally warps space-time to preserve this one absolute speed. This is what Albert Einstein realized in 1905 in his miracle year when he published his paper on the electrodynamics of moving bodies, what we now call special relativity. He took seriously 2 simple postulates. First, the laws of physics are the same in all non-accelerating reference frames. Second, the speed of light is constant for all observers. From just these 2 principles, he derived time dilation, length contraction, the relativity of simultaneity, and E equals mc. But why? Why is light speed special? Why is it constant? What makes light so damn important? Here's the answer that most people never hear. Light speed isn't special because of light. Light just happens to travel at this speed because photons are massless. The fundamental constant isn't actually the speed of light. It's the speed of causality, or the maximum speed at which information can propagate through spacetime. Light moves at this speed because it has no mass. Anything with 0 mass must move at this speed. If we discovered another massless particle tomorrow, it would also move at 299,792,458 meters per second. Light isn't special. Masslessness is special. And mass is what slows things down. Every particle with mass moves at less than light speed because mass is, in a very real sense, resistance to motion through space. The more mass something has, the more energy you need to accelerate it, and the harder it becomes to push it toward light speed. As something approaches light speed, its relativistic mass increases toward infinity, requiring infinite energy to actually reach light speed. This is why nothing with mass can reach light speed, It would require infinite energy. It's not an engineering problem we might solve someday with better rockets. It's a fundamental geometric constraint of spacetime itself. But here's where we get to the real revelation. If you have zero mass, you don't just move at light speed. You must move at light speed. There's no such thing as a slow photon or a photon at rest. The instant a photon is created, it's already moving at 299,792,458 meters per second, and it will continue at exactly that speed until it's absorbed. And this brings us to the absolutely mind-breaking consequence. Because photons move at light speed, and time stops at light speed, photons don't experience time. From a photon's perspective, if we can even use that phrase, emission and absorption happen simultaneously. The journey never happens. Let me make this concrete. Right now, look at your hand. The light bouncing off your skin traveled from your hand to your retina maybe a foot or two. From your perspective, that took a few nanoseconds. But from the photon's perspective, zero time. The photon was emitted from your hand and absorbed by your retina in the same instant. Now look at the sun. Don't actually look directly at it, but you know what I mean. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. But from any individual photon's perspective, zero time. It's emitted in a fusion reaction in the sun's core, travels 93 million miles through space, and is absorbed by your eye in a single timeless instant. Now let's go extreme. The Andromeda galaxy is 2.5 million light years away. The photons from Andromeda that enter your eye tonight left that galaxy 2.5 million years ago, long before humans existed. But from those photons' perspective, zero time. From their perspective, they're emitted and absorbed in the same eternal now. The most distant light we can see comes from the cosmic microwave background, the afterglow of the Big Bang itself, about 13.8 billion years ago. From our perspective, those photons have been traveling for 13.8 billion years, crossing an expanding universe, witnessing the formation of galaxies, stars, planets, and eventually you. But from the photons' perspective, zero time has elapsed. They were emitted in the hot, dense early universe and absorbed by your radio telescope in the same instantaneous moment. Think about what this means. Every photon that has ever existed experiences the entire history of the universe as a single moment. The Big Bang and the heat death of the universe are simultaneous from light's perspective. All of time collapses into a single point of now. And here's the really disturbing question this raises. If time is zero from light's perspective, and light connects every point in the universe, does time fundamentally exist at all? Or is time just something that emerges from massive particles for anything that moves slower than light speed? We need to go deeper into what time actually is, because the more you examine it, the weirder it gets. You think you know what time is. It's what clocks measure, right? It's the thing that flows from past through present into future. It's the reason you can remember yesterday, but not tomorrow. It's what prevents everything from happening at once. But here's the problem. Nowhere in the fundamental equations of physics does time actually flow. The equations are time-symmetric. They work just as well running backward as forward. If you filmed fundamental particles interacting and played the film in reverse, you couldn't tell the difference. The laws of physics don't care which direction is forward in time. This is deeply disturbing when you think about it. Our most complete description of reality quantum field theory combined with general relativity doesn't include the passage of time as a fundamental feature. Time appears in the equations. This is called the Poincare recurrence theorem, and it tells us that given infinite time, any closed system will eventually return to any previous state. Your broken egg will eventually reassemble itself, atom by atom, purely by chance. You just have to wait longer than the current age of the universe, multiplied by itself, a googolplex times. So the arrow of time, the sense that time flows in one direction, isn't fundamental, it's statistical. It's an artifact of the fact that the early universe started in an extremely low entropy state for reasons we don't fully understand, and entropy has been increasing ever since. We call the low entropy direction past and the high entropy direction future, but the equations don't care. Physicist Carlo Rovelli puts it this way: time is ignorance. What we experience as the flow of time is actually just our ignorance about the complete microstate of the universe. If we knew the exact position and momentum of every particle, we wouldn't experience time at all. We'd see the universe as a timeless, deterministic block where past, present, and future all exist equally. And this brings us to one of the most controversial ideas in modern physics: the block universe. Imagine space-time not as a stage on which events happen, but as a four-dimensional object, a solid, unchanging, eternal block. Every moment that has ever existed or will ever exist is equally real, equally present, existing simultaneously in this block. Your birth, your childhood, this moment right now, your death, and everything that happens after all of it exists right now, frozen in the geometry of space-time. You're not moving through time. You can't move through time because you exist at all times. What you experience as now is just your consciousness reading out one time slice of your four-dimensional world line, the path you trace through space-time from birth to death. Think of it like a movie on a DVD. The entire movie exists simultaneously on the disc. The beginning, middle, and end are all equally present. Nothing is moving or changing. But when you play the DVD, you experience it as a sequence one frame after another, creating the illusion of motion and change. Your consciousness is like the DVD player, reading out sequential slices of a static spacetime and creating the subjective experience of time flowing. In the block universe view, nothing ever changes because change requires time, and time is just another dimension like space. You don't change in time any more than you change in space. You simply extend through time, just as you extend through space. This view follows naturally from special relativity. Remember, simultaneity is relative. What counts as now depends on your velocity. Two observers moving at different speeds will disagree about which distant events are happening now. There's no absolute, universal present moment that applies to the whole universe. Each observer has their own present, their own slice of the block. And if there's no universal now, then past and future can't be fundamentally different from present. They're all just different locations in space-time, like north and south are different locations in space. Your childhood isn't gone, it's back there in time, just as real as it ever was, just as England is over there in space. You can't visit your childhood any more than you can instantly teleport to England, but it exists. Julian Barber, a British physicist who's devoted his career to understanding time, takes this even further. He argues that time doesn't exist at all, not even as a dimension. In his view, the universe is a vast collection of possible configurations, what he calls nows, and what we experience as time is simply a path through this space of configurations. The universe doesn't evolve in time. It simply exists as a timeless whole, and consciousness creates the illusion of sequence by stringing together correlated nows. This is starting to sound mystical, but it's grounded in real physics. When physicists try to apply quantum mechanics to the universe as a whole, creating what's called quantum cosmology, they run into a huge problem called the problem of time. The fundamental equation of quantum cosmology, the Wheeler-DeWitt equation, doesn't contain time at all. It describes a universe in which nothing changes, nothing evolves. Time disappears entirely at the quantum level when you try to describe the whole universe. This has led some physicists, including people like Rovelli and Lee Smolin, to conclude that time must be an emergent phenomenon, something that appears at large scales but isn't fundamental. Like wetness emerges from water molecules, but isn't a property of individual molecules. Now here's where we connect all of this back to light. If time is emergent, if it's something that only appears from massive particles moving slower than light speed, and light exists outside of time. Light doesn't experience time because light is traveling at the speed at which time emerges. Let me put this another way. Space-time has a structure, a geometry. That geometry includes what physicists call light cones. Imagine you're at a point in space-time right here, right now. There are events in your past that could have influenced you, events inside your past light cone. And there are events in your future that you could influence events inside your future light cone. But there are also vast regions of space-time that are outside your light cone entirely. Events that are too far away for light to have reached you yet, or events that are so far away you can never influence them, even if you send signals at light speed for the rest of time. The boundaries of your light cone, the edges that separate what can influence you from what can't, are defined by light. Light itself travels exactly along the edge of the light cone, along what's called a null geodesic. And here's the crucial bit. The proper time along a null geodesic, the time experienced by something traveling along it, is exactly 0. Light doesn't move inside space-time like massive particles do. It moves along the boundary between past and future, between cause and effect. It exists at the interface where time emerges. Think of it this way. Massive particles like you and me are trapped inside the light cone. We're moving through time, experiencing seconds and minutes and hours, getting older, moving from past to future. But light isn't inside the cone. It is the cone. It defines the structure of causality itself. This is why nothing can travel faster than light. It's not about light being fast. It's about light being the boundary of causality. If you could send a signal faster than light, you could send information outside your light cone, which means you could influence events that are in your absolute past according to some reference frames. You could, in principle, send messages backward in time, creating causal paradoxes. But here's where it gets really mind-bending. If time stops at light speed, and faster than light travel would mean going backward in time, then what does it mean to go faster than the speed at which time stops? How do you move through space faster than the speed at which there is no time? The answer is, you can't, because the question doesn't even make sense. Faster than light travel isn't prohibited by some cosmic speed limit posted on the edge of the universe. It's prohibited by the logical structure of space-time itself. Moving faster than light is like trying to go north of the North Pole. It's not hard. It's meaningless. Unless, of course, you break space-time itself. And that's exactly what certain solutions to Einstein's equations allow. Wormholes, shortcuts through space-time, connecting distant points, could theoretically allow you to arrive somewhere faster than light could get there by taking the long way. But you wouldn't be moving faster than light locally. You'd be taking a shortcut through a folded space-time. Similarly, the Alcubierre drive, a hypothetical warp drive, would work by contracting space in front of a ship and expanding it behind, allowing the ship to surf a wave of space-time while remaining at rest locally. These solutions are mathematically valid, but they require exotic matter with negative energy density, which may or may not exist. Even if they do work, you still never locally exceed light speed. You're warping space-time to change what local means. But all of this brings us back to the central mystery. Why is light speed the cosmic speed limit? Why is it the speed of causality? Why does time stop there? And the answer, I think, is that we're asking the wrong question. Light speed isn't the speed at which time stops. Time stopping is what it means to move at light speed. These aren't two separate phenomena where one causes the other. They're two ways of describing the same geometric feature as spacetime. Spacetime has a structure called a metric that defines distances and time intervals. This metric has a special property. There are paths through spacetime where the spacetime interval is zero, no distance, no time. These are null geodesics, the paths that light follows. Light doesn't experience zero time because it's moving fast. Light moves along null geodesics, and null geodesics are defined as paths with zero proper time. It's like asking why the surface of a sphere is curved. It's not that some force is bending it. Curvature is what it means to be a sphere. Similarly, zero proper time is what it means to be a light-like path through spacetime. So let's take a step back and ask the question we've been circling around. Does time collapse into light? And what could that even mean? One interpretation is what we've been discussing. From light's perspective, time is zero, collapsed down to a point. The entire history of the universe, 13.8 billion years from our perspective, is experienced by a photon as a single, instantaneous moment. In this sense, yes, time collapses into light. All of temporal experience is compressed to nothing at light speed. But there's a deeper interpretation, one that gets at the fundamental structure of reality. Maybe time as we experience it flowing, directional, separating past from future, doesn't exist in the fundamental laws of nature. Maybe time is something that emerges from our interaction with light and causality. Here's what I mean. You can only see the past. By the time light from an object reaches your eyes, that object has moved on. When you look at the sun, you're seeing it as it was 8 minutes ago. When you look at Andromeda, you're seeing it as it was 2.5 million years ago. The very act of seeing is an interaction with the past, mediated by light. Your entire experience of now is actually a collection of many different thens from different distances, all stitched together by your brain into a coherent present. But that present is an illusion. It doesn't exist in any objective sense. What exists is a web of light rays carrying information about the past and your brain's model of that information. In a sense, light is the carrier of time. It brings the past into the present. It connects distant events in your light cone to your current moment. Without light, without something traveling at the cosmic speed limit, carrying causal information, there would be no way to experience time at all. This is what physicist John Wheeler meant when he talked about the participatory universe. The universe isn't just something we observe passively, sitting outside of it. We're part of the universe, interacting with it through light and other forces. And our observations literally define what we mean by now and here. Reality isn't a pre-existing stage on which events happen. It's a network of interactions, most of which are mediated by light. Wheeler illustrated this with his famous delayed choice experiment. Take the classic double-slit experiment. Shine light through two slits, and it creates an interference pattern on a screen behind them, proving that light behaves as a wave passing through both slits simultaneously. But if you put detectors at the slits to see which one the light goes through, the interference pattern disappears, and light behaves like a particle going through one slit or the other. Wheeler asked, what if you wait until after the light has passed through the slits, and then decide whether to measure which slit it went through? Can you retroactively change whether it behaved as a wave or particle? The answer, confirmed by experiments in the 1980s, is yes. Your measurement choice now affects what happened in the past. Not because you're literally reaching back in time, but because what happened isn't determined until an interaction occurs. Before the measurement, there's no fact of the matter about which slit the light went through. Reality is undefined. Only when light interacts with a detector, when information becomes actualized through an interaction, does what happened become real. This is quantum mechanics, and it's weird, but here's the connection to time. If reality is defined by interactions, and interactions are mediated by light traveling at the cosmic speed limit, then time itself is the process of these interactions happening. Time is information propagating through spacetime at light speed. Time is the universe figuring itself out, one interaction at a time. And from light's perspective, there's nothing to figure out. All interactions are simultaneous. The question and the answer occur in the same instant. Emission and absorption are one event, not two. There is no time because there's no gap between cause and effect. So does time collapse into light? Maybe the right way to say it is, time emerges from light. Time is what happens when information travels at finite speed. Time is the lag between cause and effect, the delay between question and answer. And light, traveling at exactly the speed where time becomes zero, sits at the boundary where time emerges. This might sound abstract, but it has profound implications. It means that the flow of time you experience, your memory of the past, your anticipation of the future, your sense of the present moment, all of this is a consequence of the fact that you're made of massive particles moving slower than light speed, interacting with other massive particles through the exchange of light and other force carriers. If you were a photon, you wouldn't experience time. You'd exist in an eternal now, all of your existence simultaneous. But you're not a photon. You're a slow, massive, classical being, and so you experience time. You're trapped in the flow, watching one moment after another, unable to see the eternal now that light sees. But here's the beautiful part. Because you can think about this, because you can understand what light's perspective would be, you can in some sense glimpse that eternal now. You can understand, intellectually, if not experientially, what it would be like for time to not exist. And that understanding changes how you relate to your own experience of time. Let's get concrete about something that's probably bothering you. If time stops at light speed, how does light even move? If no time passes for a photon, how does it get from the sun to the Earth? How does it travel 93 million miles if it doesn't experience any duration? This is the paradox at the heart of light's relationship with time, and resolving it requires understanding that motion and time are observer-dependent concepts. From your perspective, watching from Earth, the photon absolutely moves. It travels 93 million miles over 8 minutes and 20 seconds. You can track its progress, measure its velocity, watch it arrive. But from the photon's perspective, and this is where language breaks down because photons don't have perspectives in any meaningful sense, there is no journey. The photon exists in a state where emission and absorption are the same event. It doesn't experience traveling any distance because the distance is Lorentz contracted to zero along its direction of motion. Remember length contraction? As you approach light speed, distances shrink in your direction of travel. At light speed, distances shrink to exactly zero. From the photon's perspective, the entire universe along its direction of travel is compressed to a single point. The sun and the Earth are in the same place. There's no distance to cross, no time needed to cross it. This is completely insane, and yet it's exactly what the mathematics of special relativity tells us. Both perspectives are valid, yours where the photon moves, and the photon's where it doesn't. There's no contradiction because motion is relative. What counts as moving depends on your reference frame. But here's where we need to be careful. Technically, photons don't have a valid reference frame. You can't boost yourself to light speed using the Lorentz transformation, because the transformation breaks down, you'd be dividing by zero. So when I say from the photon's perspective, I really mean in the limit as you approach light speed, which asymptotically approaches zero time and zero distance. This is related to a deeper issue. Quantum field theory, our most complete description of light and matter, doesn't actually describe the world from photons' perspective. It describes how fields interact, and light is a quantum of the electromagnetic field. Photons don't have internal experiences, any more than ripples in a pond have internal experiences. They're excitations in a field, patterns of energy propagating through space. But those patterns propagate at a very special speed, the speed at which the space-time interval is zero. And that's the key insight. Light doesn't experience time, not because it's a special substance, but because it's traveling along a special type of path through space-time, a null path where the geometry of space-time itself makes time undefined. Now let's connect this to something even more mind-bending. If light defines the structure of causality, and causality is what gives us the arrow of time, then light literally creates time, not metaphorically literally. Before the Big Bang, when the universe was infinitely dense and hot, light and matter were in thermal equilibrium, constantly interacting. Photons couldn't travel more than a tiny distance before being absorbed and re-emitted. The universe was opaque to light. Then, about 380,000 years after the Big Bang, the universe expanded and cooled enough that atoms could form. Suddenly, light could travel freely without being immediately absorbed. This moment is called recombination, and it's when the cosmic microwave background was emitted. The universe became transparent to light. And this is when time, in a very real sense, became meaningful. Before recombination, causality was local. Nothing could influence anything far away because light couldn't propagate. After recombination, light could connect distant parts of the universe. Information could flow, structure could form. The universe could become complex. Some physicists have argued that this is when time itself became well-defined. Before recombination, the universe was so dense and hot that quantum effects dominated, and in the quantum realm, time is fuzzy and uncertain. Only when the universe cooled and became classical did time become the smooth, flowing thing we experience. This is speculative, but it points to something profound. The relationship between light, causality, and time isn't accidental. It's fundamental to the structure of reality. Light is the carrier of causality. Causality defines the arrow of time, and time is the dimension in which change happens. Remove light, remove the cosmic speed limit, and the whole structure collapses. But we're still dancing around the really hard question. What is time, fundamentally? Is it real, or is it an illusion? Does it flow, or does it just exist? Is it a dimension like space, or is it something else entirely? Let me tell you about one of the strangest proposals in modern physics. Time might be an illusion created by quantum entanglement. This is the work of physicists like Doane Page, Seth Lloyd, and more recently, a team at NIST led by physicist Samuel Braunstein. The idea is radical. Maybe time emerges from the quantum correlations between particles. Here's the basic idea. Quantum mechanics allows particles to become entangled, meaning their properties are correlated in ways that can't be explained by classical physics. When two particles are entangled, measuring one instantly affects the other, regardless of distance. Einstein hated this, calling it spooky action at a distance, but it's been experimentally verified thousands of times. Entanglement is real. Now here's the wild part. Entanglement creates correlations between different parts of a quantum system. And correlations are information about relationships. What if time is just another form of correlation? What if the flow of time is actually the process of quantum systems becoming entangled with their environment, creating more and more correlations as entropy increases? In this view, the arrow of time, the sense that time flows from past to future, emerges from the growth of entanglement. The early universe had very little entanglement. Particles were mostly independent. As the universe evolved, particles interacted, became entangled, and correlations spread throughout the cosmos. That spreading of quantum correlations is what we experience as time. This would explain why time has a direction. Entanglement naturally increases because there are vastly more ways for particles to be entangled than unentangled, just as there are more ways for eggs to be broken than whole. The second law of thermodynamics, entropy, always increases, would be a consequence of quantum entanglement always increasing. And here's where it connects to light. Entanglement spreads at the speed of light. When two particles interact and become entangled, that correlation can't propagate faster than light speed. If you entangle two particles here and then separate them, the correlation between them exists, but you can't use it to send information faster than light. The correlations are bounded by light cones. So if time is the spread of quantum correlations, and those correlations propagate at light speed, then time is literally defined by light. The rate at which time flows is set by how fast quantum information can propagate through space, which is light speed. From this perspective, Time doesn't collapse into light. Time is made of light. Time is the flow of quantum information through spacetime at the cosmic speed limit. And photons, traveling at that limit, experience zero time because they're surfing the wave of information propagation itself. They're not inside the flow. They are the flow. This is deeply weird, and it's not yet mainstream physics, but it's gaining traction. In 2013, physicist Joan Vaccaro published a paper arguing that the arrow of time emerges from quantum entanglement and the breaking of a symmetry called T-symmetry. In 2017, physicists at the University of Vienna experimentally demonstrated that quantum entanglement does increase over time in isolated systems, exactly as this theory predicts. If this is right, it means that your experience of time flowing is a consequence of your brain becoming increasingly entangled with your environment. Every perception, every memory, every thought creates new quantum correlations between your neurons and the outside world. That accumulation of correlations is what you experience as time passing. And light is the messenger carrying those correlations. When you see something, photons bouncing off that object enter your eye, are absorbed by molecules in your retina, create chemical reactions that trigger nerve impulses, and eventually change the quantum state of neurons in your brain. You've become entangled with the object through the mediation of light. That entanglement is irreversible. You can't unsee something, and that irreversibility is the arrow of time. So when I asked earlier whether time collapses into light, maybe the answer is more subtle. Time and light are two aspects of the same underlying process. Light is quantum information in motion. Time is the accumulation of that information. They're not separate things. They're different views of the same fundamental feature of reality. Now I want to blow your mind with something most people never learn about. There are situations where time genuinely does weird, non-linear things, and light is involved in all of them. We've been talking about special relativity, but we haven't touched on general relativity, Einstein's theory of gravity. And in general relativity, things get way stranger. Special relativity tells us that time slows down when you move fast. General relativity tells us that time also slows down in gravitational fields. The stronger the gravity, the slower time passes. This is gravitational time dilation, and it's been measured countless times. The classic experiment was in 1976, when NASA launched a rocket 10,000 kilometers into the air, carrying an atomic clock. The clock experienced weaker gravity than clocks on the ground, and when the rocket returned, the flying clock had measured more time. It had ticked faster because it experienced less gravitational time dilation. The difference exactly matched Einstein's predictions. But here's where it gets really crazy. Near a black hole, gravitational time dilation becomes extreme. At the event horizon, the point of no return time slows to a stop relative to a distant observer. If you watched someone fall into a black hole, you'd see them slow down as they approach the horizon, becoming more and more redshifted, dimmer and dimmer, asymptotically approaching the horizon, but never quite reaching it. From your perspective, they take infinite time to cross the horizon. But from the falling person's perspective, they cross the horizon in finite time, maybe just seconds. They don't notice anything special happening at the horizon itself. Time passes normally for them. It's only relative to the outside universe that their time has stopped. This is exactly analogous to what happens with light. Just as time stops for light relative to slower observers, time stops at the event horizon relative to distant observers. The black hole's gravity is so strong that the escape velocity equals light speed, and anything at that boundary, including time itself, is frozen from the outside perspective. Now here's the really disturbing part. We can calculate what happens to light near a black hole. Photons emitted from near the event horizon get redshifted. Their wavelength stretches out as they climb out of the gravitational field. The closer to the horizon they were emitted, the more they're redshifted. Photons emitted right at the horizon are infinitely redshifted. Their wavelength becomes infinite, their energy zero. They're still traveling at light speed, but they're frozen in place relative to distant observers, unable to make progress outward. This means that light emitted from the event horizon takes infinite time to escape from the perspective of a distant observer. Time has stopped, not just for massive objects, but for light itself. The horizon is a place where even light can't move forward through space, because the curvature of spacetime is too extreme. Physicist Kip Thorne, who won the Nobel Prize for detecting gravitational waves, describes this beautifully. The event horizon is a frozen star, a surface where everything matter, light, time is frozen in place from the outside view, even though it's moving normally from the inside view. It's like a one-way mirror in time. You can see in, but you can't see out. And this brings up one of the deepest puzzles in physics, the black hole information paradox. When something falls into a black hole, it takes all of its information with it, the quantum states of all its particles, everything that describes it. But from the outside, we can't see that information anymore. It's hidden behind the horizon. So is the information destroyed? Or is it somehow preserved? Hawking initially argued that information is destroyed, which would violate quantum mechanics. But later research suggests that information is somehow encoded on the event horizon itself, possibly in a holographic form. The idea is that the three-dimensional volume of the black hole can be completely described by two-dimensional information on its surface. This is called the holographic principle, and it's one of the strangest ideas in modern physics. If the holographic principle is correct, then reality as we know it, 3 dimensions of space and 1 of time, might itself be a kind of hologram, a projection of information encoded on a distant boundary. Time and space might not be fundamental. They might be emergent from more basic information theoretic principles. And light plays a crucial role in this. In the holographic principle, light rays null geodesics define the structure of spacetime. The boundaries of regions, the horizons of black holes, the surfaces where information is encoded, all of these are defined by light. Light isn't just moving through spacetime. It's defining what spacetime is. This is why some physicists, like Leonard Susskind and Gerard T. Hooft, have argued that spacetime itself might be an emergent phenomenon, and that at the deepest level, reality is made of quantum information organized in a way we don't yet understand. Time would be an illusion, space would be an illusion, and light would be the projection mechanism that creates those illusions. Let me bring this back to something you can actually feel, your perception of time right now. You've been watching this video for over an hour, but has time been flowing uniformly for you? Have you noticed that some sections seem to fly by while others dragged? That's not just psychology, it's physics. Your brain doesn't experience time directly. It constructs a sense of time from memory, attention, and prediction. When you're bored, you're not getting much new information, so your brain doesn't create many memories, and looking back, it feels like no time passed. When you're engaged, forming memories rapidly, it feels like time is passing quickly in the moment. But when you look back, you remember it as taking a long time because you have so many memories. This is why childhood feels like it lasted forever, but each year as an adult seems faster. You're forming fewer novel memories as you age. Your brain is laying down less information, so it retrospectively constructs less time. But here's the connection to physics. Your brain's construction of time is fundamentally about information. How much information did you process? How many new patterns did you encode? How many quantum correlations did your neural networks form? That's what creates your subjective sense of duration. And all of that information processing is mediated by light. The photons entering your eyes, the chemical reactions in your neurons, the electrical signals propagating through your brain, all of this is bound by the cosmic speed limit. Information can't flow through your brain faster than light speed, which means your thoughts, your perceptions, your sense of self, all of it is constrained by the same limit that makes time zero for photons. In a very real sense, You are a pattern of information propagating through spacetime at less than light speed, and your consciousness is the experience of that propagation from the inside. Time feels like it flows because information is flowing through your brain, creating new patterns, new correlations, new memories. You are time, experiencing itself. And this raises a profound question. If you could speed up your brain's information processing, if you could think faster, would time feel slower? Yes, actually. This is why time seems to slow down in emergencies. When you're in a car accident or falling from a height, your brain kicks into high gear, processing information much faster than normal, encoding memories at a higher rate. Looking back, you remember it as taking longer than it actually did because you formed more memories per second of real time. Drugs can do this too. Stimulants like caffeine and amphetamines speed up neural processing, making time feel slower. Depressants like alcohol slow it down, making time feel faster. Your subjective experience of time is literally variable depending on your brain's information processing rate. Now imagine if you could process information at light speed. What would time feel like then? The answer is, it wouldn't. At light speed, there's no subjective experience of duration, no flow, no passage. You'd experience your entire existence as a single moment, exactly like a photon does. This is pure speculation, but some physicists have wondered whether this might be what happens to consciousness at death. If consciousness is a pattern of information, and that pattern stops propagating through time, stops updating, stops forming new correlations, does it collapse into a single timeless moment? Does your entire life become simultaneous, experienced as an eternal now? There's no way to know, of course. But the mathematics of relativity says that from your perspective, your entire life already is an eternal now, a four-dimensional world line stretching from birth to death, all existing simultaneously in the block universe. It's only from inside, reading out sequential slices, that it feels like time is flowing. And maybe death is just the end of that sequential readout. The DVD stops playing, but the entire movie still exists on the disc. Your life doesn't disappear when you die. It just stops being read out. All of it, every moment, every experience, every thought remains in the space-time structure, timelessly real. This isn't mysticism or religion, but we need to address the elephant in the room: quantum mechanics. Everything I've said so far assumes classical relativity, a smooth, continuous space-time where light follows well-defined paths. But we know that's not the whole story. At small scales, quantum mechanics takes over, and things get weird in entirely new ways. In quantum mechanics, light isn't just a wave or a particle. It's both, depending on how you look at it. This is wave-particle duality, and it's fundamental to understanding what light actually is. When you're not looking, light behaves like a wave, spreading out, interfering with itself, passing through multiple paths simultaneously. But when you measure it, it behaves like a particle, a photon, with a definite position and energy. This isn't because we're disturbing it with our measurements, as early interpretations suggested. It's because wave and particle are both incomplete descriptions. Light is a quantum field, and what we call photons are excitations in that field. The field is what's real. The photons are how we interact with it. And here's where time gets even weirder. In quantum mechanics, particles don't have definite properties until you measure them. Before measurement, a photon doesn't have a definite position or momentum. It exists in a superposition of many possibilities. Only when it interacts with a detector does it collapse into a definite state. But remember, photons don't experience time. So from the photon's perspective, emission and absorption, the creation of the superposition and its collapse are the same event. The photon never exists in superposition from its own perspective because it doesn't have a perspective extended through time. It's born and dies in the same instant. This raises a question that physicists are still grappling with. If photons don't experience time, do they experience superposition? Does it even make sense to talk about a photon being in a superposition from its own frame of reference? The answer seems to be that superposition is inherently a time-dependent concept. It's about the evolution of quantum states through time. And if there's no time, there's no evolution, no superposition. The photon simply connects an emission event to an absorption event, and all the quantum weirdness, the interference, the superposition, the uncertainty, is how we describe that connection from our time-bound perspective. This connects to something called the transactional interpretation of quantum mechanics, developed by physicist John Cramer. In this view, quantum events involve both a forward-in-time wave from the emitter and a backward-in-time wave from the absorber. The two waves meet in the middle and create a transaction, a handshake across time, and that's what we observe as a particle traveling from source to detector. This sounds insane waves going backward in time, but it actually works mathematically and explains some of the weirdest features of quantum mechanics, like entanglement and delayed choice experiments. And crucially, it makes sense for photons. If photons don't experience time, then forward and backward in time don't mean anything from their perspective. The photon connects emitter and absorber timelessly, and we parse that timeless connection as a time-ordered sequence because that's how our brains work. Physicist Carlo Rovelli has developed this idea further in his theory of relational quantum mechanics. He argues that quantum states are not absolute, but relational. They're relative to the observer. Just as velocity is relative in special relativity, quantum states are relative in quantum mechanics. A photon doesn't have a definite state. It only has states relative to systems that interact with it. And if states are relational, then so is time. Time isn't an absolute background against which events happen. It's a relation between events. The photon relates its emission event to its absorption event, and that relation is what we call its trajectory. But the photon itself doesn't experience the relation from the inside because it's the relation. You can't step outside a relation and observe it. You can only observe relations you're not part of. This is getting deeply philosophical, but it points to something profound. Time might be fundamentally relational, not absolute. Time is the structure of causal relationships between events, and light is the carrier of those relationships. When photons don't experience time, they're not experiencing the relationships they themselves embody. They are the relationships. We're now 2 hours into this exploration, and I want to step back and connect everything to your life. Why does any of this matter? Why should you care that time stops at light speed, that photons experience zero duration, that time might not be fundamentally real? Here's why. Understanding time changes how you experience time. Once you grasp that time is not absolute, not universal, not even necessarily fundamental. Once you understand that your experience of time is constructed by your brain from patterns of information bound by light speed, you can't go back to thinking about time naively. Every moment you experience is a construction. Your now is not the same as my now if we're moving relative to each other. The stars you see tonight might have died thousands of years ago, but their light is reaching you now, making them present to you even though they're past. Your memories are not the past. They're patterns in your brain right now, in the present, telling a story about the past that might not even be accurate. And the future? The future doesn't exist yet, except perhaps in the block universe view, where it exists just as much as the present. But you can't access it, can't see it, because light hasn't brought it to you yet. You're trapped in an expanding bubble of causality, a light cone spreading outward from your birth, and you can only interact with events inside that bubble. This should be profoundly humbling. You're not standing outside time, observing it flow past you. You're embedded in time, a pattern of information being written into the structure of space-time at less than light speed. You're a slow, massive, time-bound creature watching a universe that, from light's perspective, is timeless and eternal. But here's the empowering part. You're conscious of this. You can think about time, understand time, even transcend time conceptually, if not physically. No photon can do that. Photons just exist, timelessly connecting emission to absorption. But you can know about light's timeless perspective and your time-bound one simultaneously. You can hold both views in your mind and understand how they relate. That's extraordinary. That's what consciousness gives you. You're the universe experiencing itself from the inside, and in doing so, you're creating time itself through your observations, your memories, your thoughts. You're not just in time, you're making time by being conscious. Every moment of attention, every memory you form, every choice you make, these are acts of creation. You're laying down the flow of time through your existence. You're turning the timeless block universe into a lived story with a beginning, middle, and end. You're writing time into reality through the act of living. And light is your connection to the rest of reality. Every photon that enters your eye is a messenger from the past, a carrier of information about events that happened seconds or years or billions of years ago. You're receiving messages from across the cosmos, assembling them into a model of reality, making sense of the universe one photon at a time. When you look at the night sky, you're not just seeing stars, you're seeing history. You're seeing the universe as it was, layer upon layer of past moments, all arriving at your present. The moon's light is 1.3 seconds old. Jupiter's light is 40 minutes old. Sirius's light is 8.6 years old. Andromeda's light is 2.5 million years old. You're seeing multiple pasts simultaneously, all because light travels at finite speed. And that finite speed, that cosmic speed limit, is what creates your experience of time. If light were infinitely fast, if information could propagate instantaneously, there would be no time, no causality, no flow. The universe would be a single simultaneous instant. But light is finite, and so time emerges, and so you exist as a temporal being, experiencing moments sequentially, unable to see the whole at once. This is what it means to say that time collapses into light. Light is the boundary condition for time. At light speed, time collapses to zero. Below light speed, time emerges. And you, moving through space-time at a tiny fraction of light speed, experience time flowing because you're so far from that boundary. Let me take you even deeper. There's a theory in physics called the holographic principle that suggests the entire universe might be a hologram, three-dimensional projection of information encoded on a two-dimensional surface. This sounds like science fiction, but it comes from serious theoretical work on black holes and string theory. The idea started with black hole thermodynamics. In the 1970s, Stephen Hawking and Jacob Bekenstein discovered that black holes have entropy, a measure of disorder, and that entropy is proportional to the surface area of the event horizon, not the volume inside. This was shocking because entropy usually scales with volume. A box with twice the volume has twice the entropy. But black holes don't work that way? This suggests that all the information inside a black hole is somehow encoded on its two-dimensional surface. The three-dimensional interior is somehow redundant, a projection of the surface. Leonard Susskind and Gerard T. Hooft took this further and proposed that maybe the entire universe works this way. Maybe all of space-time is a hologram, with the fundamental information living on a distant boundary, and everything we experience being a projection of that information. In string theory, this is made precise through something called the ADS-CFT correspondence, discovered by Juan Maldacena in 1997. It's a mathematical duality showing that a theory of gravity in a higher dimensional space is equivalent to a quantum field theory on the boundary of that space. The interior and the boundary describe the same physics. They're two different languages for the same reality. If the holographic principle is correct, then space and time as we experience them are not fundamental. They're emergent from some deeper information structure. And crucially, light plays a central role because holography is formulated using light rays. The holographic screens where information is encoded are defined by null surfaces swept out by light rays. So once again, we find that light is the key to understanding time and space. Light defines the structure on which reality is encoded. Time might not be fundamental. It might be a holographic projection, and light is the projector. This is still speculative. We don't have a complete theory of quantum gravity that would tell us if holography is really how the universe works. But multiple lines of evidence point in this direction. Black hole thermodynamics, string theory, quantum entanglement, quantum error correction, all of these suggest that reality is information theoretic at its core, and that spacetime emerges from that information. And if spacetime emerges, then time emerges. Time is not a fundamental feature of reality. It's something that appears at large scales, like wetness appears from water molecules or temperature appears from molecular motion. At the deepest level, there is no time, just information, just quantum states, just correlations. And photons, sitting at the boundary where time becomes zero, might be more fundamental than the time-bound reality we experience. They might be closer to the true nature of things than we are, with our slow, massive, time-trapped existence. Let's address one more deep question. Why does anything exist at all? And what does light have to do with it? This sounds philosophical, but it connects to real physics in surprising ways. The universe started with the Big Bang, a singularity, where all of space-time began. But what happened at that singularity? What existed before it? These questions might not even make sense, because before implies time, and time itself began at the Big Bang. There is no before, just as there's no north of the North Pole. But here's something interesting. At the moment of the Big Bang, the universe was infinitely dense and infinitely hot. Under those conditions, particles and antiparticles were constantly being created and annihilated, and matter and radiation particles and photons were in thermal equilibrium. Everything was light, in a sense. The universe was a soup of photons and particles, all moving at or near light speed, all experiencing minimal time dilation. As the universe expanded and cooled, particles slowed down relative to light speed. They became massive, time-bound, experiencing time's flow. But photons remained at light speed, timeless as always. The cosmic microwave background, the oldest light we can see, is the leftover radiation from that hot early universe, now cooled to just 2.7 degrees above absolute zero, but still traveling at light speed, still experiencing zero time. Those photons were emitted 380,000 years after the Big Bang, but from their perspective, no time has passed. They're still in that hot early universe, even though from our perspective, 13.8 billion years have elapsed. The early universe and the present moment are simultaneous for those photons. This raises a fascinating possibility. Maybe the Big Bang itself, from the perspective of light, is still happening. Maybe the entire history of the universe, from beginning to end, is a single moment from light's perspective, a timeless block where creation and destruction are the same event. Some physicists have speculated about this. In certain cosmological models, the universe is cyclically expanding, contracting, bouncing, expanding again in an endless cycle. Each cycle lasts trillions of years from our perspective. But from light's perspective, all cycles are simultaneous. The universe is not cyclic. It's eternal, with all cycles existing at once in a timeless whole. Other physicists, like Julian Barber, have suggested that time doesn't exist at the cosmological scale at all. The universe is a collection of possible configurations. Barber calls them nows, and what we experience as time is just a path through these configurations. The universe doesn't evolve. It simply is, and consciousness creates the illusion of evolution by experiencing correlated nows in sequence. In this view, the Big Bang isn't an event in time. It's a boundary condition on the space of all possible configurations. It's where the path starts, but it doesn't happen, because happening requires time. And time is the path itself, not something the path moves through. This is getting very abstract, but it points to something important. At the largest scales, just like at the smallest scales, time becomes meaningless. Time is a middle-scale phenomenon, something that emerges between the quantum realm and the cosmic realm, in the messy classical world where we live. And light, existing at the boundary where time stops, connects all scales. Photons from the Big Bang, photons from distant galaxies, photons from your phone screen, all of them experience zero time. All of them connect past and present and future into a single timeless network. We're approaching 3 hours now, and I want to bring this to a conclusion that ties everything together and gives you something to take into your life. We've covered massive ground: special relativity, time dilation, the block universe, quantum mechanics, black holes, holography, cosmology. Let me synthesize it into a coherent picture. Time, as you experience it, is not fundamental. It's an emergent phenomenon arising from several factors: your motion through spacetime, and much less than light speed, the growth of entropy and quantum entanglement as the universe evolves, the information processing limitations of your brain, and the finite speed of light setting a maximum rate for causal interactions. Light sits at the boundary of this emergence. At light speed, all the factors that create time disappear. Proper time becomes zero. Entropy is undefined for a single photon. Quantum correlations propagate, but aren't experienced. And information transmission happens instantaneously from the photon's perspective. This means light is the link between the timeless fundamental reality and the time-bound emergent reality we experience. Photons are messengers from the eternal now, carrying information across the void, creating the causal structure that we perceive as time's flow. When we ask, does time collapse into light? The answer is yes, in multiple senses. First, literally, at light speed, time dilates to zero. From any photon's perspective, its entire existence, from emission to absorption, is a single instant. Second, structurally, light defines the causal structure of space-time through light cones. The boundaries of past and future, the limits of what can influence what, are all defined by light propagation. Third, informationally, light carries information about the past into the present. Your entire experience of the past comes through light entering your eyes. The past doesn't exist independently. It exists as light signals reaching you now. Fourth, fundamentally, if time is emergent from quantum entanglement and information propagation, and both of these spread at light speed, then time is literally made of light in a deep sense. Time is the propagation of causal information through space-time at the cosmic speed limit. So yes, time collapses into light, not metaphorically, but as a real feature of how the universe works. Light is where time emerges from timelessness, where the eternal now interfaces with the flowing river of experience. Here's what you can do with this understanding. First, practice temporal perspective taking. When you feel rushed, stressed by time, remember, you're experiencing time flow because you're processing information at a limited rate. The universe itself doesn't care about your deadlines. From the perspective of the light bouncing off this screen into your eyes, no time is passing at all. This isn't nihilism, it's liberation. Your stress about time is real, but time itself is flexible, relative, even illusory at the deepest level. Second, appreciate the present moment more deeply. Every instant you experience is constructed from light signals arriving from the past. The present isn't a knife edge between past and future. It's a thick slice of time, including light from nearby objects, nanoseconds old, and distant objects, billions of years old, all assembled into a coherent now by your brain. You're experiencing multiple times simultaneously, and your consciousness unifies them into presence. Third, recognize your creative power. You're not passively observing time flow past you. You're actively creating your experience of time through attention, memory, and interpretation. How you relate to time is a choice. You can compress it or expand it, speed through it or savor it, by changing how you process information. Fourth, feel your connection to the cosmos. Every photon that enters your eye has traveled from somewhere else, carrying information across space and time. You're receiving messages from the universe constantly. You're part of a vast network of causal relationships mediated by light. You're not separate from the universe. You're how the universe experiences itself. And finally, embrace the mystery. We still don't fully understand time. Is it fundamental or emergent? Does it really flow, or is that an illusion? Can it be reversed or branched? These are open questions. Physics has revealed how weird time is, but it hasn't resolved all the paradoxes. That's okay. You can live with mystery. You can appreciate that you're embedded in something far stranger and more beautiful than common sense suggests. The light hitting your eyes right now has collapsed billions of years of cosmic history into this single moment. The universe has written itself into your present through photons. You are made of stardust, animated by electrochemical signals propagating at less than light speed, experiencing time because you're trapped in slowness, unable to reach the eternal now that light inhabits. But you can understand light's perspective. You can know, intellectually, what timelessness would be like. And in that knowing, you transcend your temporal prison just a little. You glimpse the eternal, even while remaining in time. Does time collapse into light? Yes, and in understanding how, you've expanded your consciousness to touch something profound about reality. You're not the same person who started watching this video 3 hours ago. You've changed. You've grown. You've become slightly more aware of the miracle of existence, the strangeness of time, the beauty of light connecting all things. Thank you for taking this journey with me. Thank you for investing these hours, these constructed, emergent, relative, possibly illusory hours, in expanding your understanding. And please hit that subscribe button, because time is strange, but YouTube's algorithm is stranger. And I want these ideas to propagate through the causal network to reach other curious minds. Drop a comment telling me what blew your mind most. What concept changed how you think about time? What will you remember from this exploration? And what time is it where you are now, both chronologically and philosophically? Until next time, or rather, until our light cones intersect again, keep looking up, keep thinking deep, and remember, you're not in time. You are time, experiencing itself from the inside. And that's the most extraordinary thing in the universe.